So we've seen that we can use Taylor polynomials to approximate functions, and we've also seen that functions can be written as an infinite series, an infinite power series, called a Taylor series. And combining those two ideas together, if you're using a polynomial, notice you're truncating the series, and when you do that, what's left is called the error, because that's the difference between the function and the polynomial. Now this error can be analyzed analytically, and the formula we use and analyze where it comes from is beyond this course, so we're not going to derive it or anything, but there's value in understanding what this error could be. If we could figure out what it could be exactly, that's always ideal. But you're going to find that most of the time, the best we can do is just figure out what the maximum error could be if we were to use a certain polynomial. So if I was going to use the 5th degree polynomial on an interval, we might be interested in saying, well, what's the maximum error I could have on that interval? What's the most I could be off? And that's generally what we're going to be doing when we analyze the error. So there is something called Taylor's theorem, and that says that this error here can be written explicitly as this expression here. So it's the n, if you're using the nth degree Taylor polynomial, it's the n plus first derivative at some x value times x minus a to the n plus 1 over n plus 1 factorial. So this is almost usable as a formula in terms of the values. Like x and a and n, we will know whenever we're doing problems. It's this guy here that we won't know, because there's no instructions on how to find that c. So it's unclear how you find that c, and in fact, this is really an existence type of formula or theorem, because it doesn't show us how to find that c value. So what we're going to do instead is we're just going to figure out what this expression here, the n plus first derivative at c, what it can't be greater than. We're going to bound it. So we're going to find an upper bound for that, rather than use it directly. And all that will do is it'll change that equal sign into a less than or equal sign, and that means we'll be we won't be finding what the error is exactly, but we'll be saying, well, the error can't be more than whatever the expression evaluates to. So examples of this are coming. So I acknowledge that formula looks somewhat confusing, so that explains this here. But let's apply it to the example we used before. So we had the function sine of x. We wanted to use its 5th degree Taylor polynomial to approximate it. And let's say we wanted to do that on the interval negative pi to pi. So we're using the Taylor polynomial to approximate it on the interval negative pi to pi. So according to Taylor's theorem, we know that the error on this interval will be will equal exactly to the n plus first derivative. Well, n is 5, so here let's just state those things. N is 5. The center of this series is 0. Okay, and so we're doing the 5th derivative at some c value times, so I'm going to put an x here, x minus the center, 0. Actually, wait, I messed up. It's the n plus first derivative, so that's a 6. X minus 0 to the n plus 1, which is 6, divided by 6 factorial. So that's using Taylor's theorem directly, and the x value would be whatever x value we were interested in approximating the function on the interval negative pi to pi. So let's just figure this out. The sixth derivative of f, we can find that out pretty quickly, because sine of x is our function. The first derivative would be cosine. The second derivative would be negative sine. The third derivative would be negative cosine. The fourth would be back to sine. The fifth would be cosine. And then the sixth would be negative sine. So this is going to equal negative sine of c x to the sixth over 6 factorial. Now the thing is, we have no way of finding this, right? So we can't really use this formula. So what we're going to do instead is we're going to figure out, what does this have to be less than? What is sine of x guaranteed to be less than on the interval negative pi to pi? And we're going to use that. So you'll see coming up that we're going to break this down and instead use an alternate version of Taylor's theorem. So we saw that we can't use Taylor's theorem directly to find the exact error, but what we could do is we can find an upper bound for the error according to this theorem. Now, this theorem here, notice it looks similar to Taylor's theorem, except there's an inequality, and this m here is, if you look carefully at what it says it's an upper bound for the n plus first derivative of our function on the interval that we're interested in. So what we're going to do is we're going to take a look at that n plus first derivative. We're going to just identify what its maximum value could be on the given interval where we're approximating the function. So let's do again refer to our sine of x example. F of x is the function we want to approximate, so that would be sine of x in our case. A is the center of our series. In our case, that's 0. N is the order of the approximating polynomial. In our case, that was 5. We want to make x minus a to the n plus first as large as possible. And the reason we want to do that is because we're trying to find an upper bound for the error. And so we really want to be safe and this is especially when you're approximating a function on an interval. We want to know what's the biggest the error can be on that interval. So in order to make a claim like that, the error can never be more than 0.001. In order to make a claim like that, we really have to hedge our bets and make all the terms in the expression as big as they can possibly be given the constraints. So for us, x minus a, again a is 0. X we're going to choose, unless it's given explicitly, unless they say like approximate, sine of x, or approximate sine of like 0.3. Then x is given. But if we're given an interval, we'll choose it to make it as large as possible. So if you think about it, if x is pi, then that's going to make this expression as big as possible, because it'll be pi minus 0 to the 6th power. And so I'm just going to indicate x minus 0 to the 6th power. We want x to be pi in that case. That'll make that as big as possible. Okay, and then lastly, the n plus first derivative of x is the absolute value of the n plus first derivative. And m is going to be the biggest that can be, the maximum value that can take on the given interval. So we already saw that the 6th derivative of x was equal to negative sine, and negative sine of x is, so that I'm going to put that in absolute values, is never bigger than 1. mean, it's never bigger than 1 ever on its entire domain, but in particular on the interval negative pi to pi. So that's our m. And so now we're actually ready to use the formula. So we would say our error is less than or equal to our m value, which is 1. X minus a to the m plus 1 would be pi minus 0 to the 6th divided by 6 factorial. So in other words, our error is going to be less than pi to the 6th over 6 factorial. And that ends up being 1.334. So that means that if I use the 5th degree Taylor polynomial to approximate sine on the interval negative pi to pi, I will never be off by more than 1.334 for any x value I use on that interval. Let's try a different example. We'll use the same function, maybe a different interval. So sine of x is given as our function, and we're using the 5th degree Taylor polynomial again. And we're going to approximate it, and we're interested in the maximum value that the error could be if we're using x values in between negative 0.9 and 0.9. So we'll use the remainder estimation theorem, and we'll be calculating r sub 5 of x. So I'm rewriting technically what the error would be. Okay, so a would be the center of our series, which is 0. N is the degree of the polynomial we're using. That's a 5. X is the maximum. X is almost always going to be an endpoint on the interval, unless you're given x directly. So we're asking the question, what's the maximum error you could get when you're approximating sine of x on the interval negative 0.9 to 0.9? You'll always use an endpoint. However, if they said what is the maximum error when you're using this polynomial to approximate sine of 0.9 or 0.7, then you just use whatever x value is given. So this is going to be the absolute value of the 6th derivative of x, which we saw is the absolute value of negative sine of x. And we know that that's always less than or equal to 1, so that's what our m is. So now we're ready. So the 5th degree Taylor polynomial is going to be less than or equal to 1 times the absolute value of 0.9 minus 0 to the 6th divided by 6 factorial. And that ends up being 7.381 times 10 to the negative 4. So let me just write in words what this means. This means that for all x values in between negative 0.9 and 0.9, the difference between the difference between our fifth degree Taylor polynomial and sine of x is less than so the difference between the two on that interval will never be greater than 7.381 times 10 to the negative 4. So that's what we mean by finding an upper bound for the error. The error, no matter what x value you choose to use to approximate or sine of x on that interval in between negative 0.9 and 0.9, the error will never be more than, you'll never be off by more than 7.38 times 10 to the negative 4. So just to make a connection with the graph that we've looked at, so if you put these settings in your calculator and graph it on the indicated window, you'll get a picture like this, where that's 0.9 and that's negative 0.9. So you can see the maximum error on this interval clearly occurs at 0.9 or negative 0.9. And this y value here I just calculated, so that's the 0.9, and it's 9.384 times 10 to the negative 5. So that is that is actually the maximum error on that interval, and that is definitely less than this. So this is clearly less than what we got there. So yes, the calculator gives more precision, but at least the theoretical work that goes into using the remainder estimation theorem is valid. So the error we found here, 9.384 times 10 to the negative 5th, I mean, that's the actual maximum error, but what we said before, that the claim that the error was less than 7.381 times 10 to the negative 4 is clearly also a correct statement. So that is the remainder estimation theorem. It's a tricky idea. It requires a lot of care and practice, so just be patient with yourself and give it time, and they'll get easier. So at this point, you should try one on your own. Maybe take a few seconds or pause the video and try it. I'm going to jot down what the actual answer, what I ended up doing, and you can compare what you got. So I had A is 0 clearly, N is a 3. Since we're approximating on that interval, we're going to use x equal to 0.2, and fortunately, the n plus first derivative of x, which would be in this case, the fourth derivative, is just equal to e to the x. That's what we like about e, it's his own derivative. So on that interval, that is never going to be greater than, e to the x is an increasing function, so we're going to use m equal to e to the 0.2, because on that right-hand interval, that's the biggest e to the x could be. And so therefore my error should be less than or equal to e to the 0.2, 0.2 minus 0 to the 4, divided by 4 factorial, which is 8.143 times 10 to the negative 5th.